Hello everyone, this is Dr. Lennon, and this week we are going to be looking at 4.1 related rates. So um, basically, so this is the section related rates. So what related rates are is they are a type of word problem in calculus that we encounter. The two big ones that we will see are related rates and optimization. So basically what this is going to do is now that we have learned, let me get this off the side here. So now that we have learned the derivative rules, and implicit differentiation, we can describe how rates of different variables change with respect to one another. So we're not just saying, okay, here's variable x, find the value of variable y. Now we're saying, okay, suppose we know something about x and y, and also maybe how fast x is changing. Can you use that to determine how fast y is changing? So sometimes what comes up with these is a lot of formulas that you have from either geometry involving areas or volumes or things like that. Sometimes it may just be a function that they give to you, but let's look at a few examples today. So the first example, let's say, suppose the area of a circle is increasing at a rate of 3 meters squared per second. Determine the rate the radius is increasing. Is increasing at the moment r is equal to 1.25 meters. So basically this is going to involve our area formula from geometry for the area of a circle. So from geometry, we know the area is equal to pi r squared. So what are we given? So in this formula, we're thinking about both variables a and r as implicit functions of another variable time, because we're wanting to know how fast they change with regard to time. So basically we're given, and I like to use Leibniz notation for these. So rather than a prime and r prime, I'll use dA dt and dr dt. I suppose you can do it the other way as well. It just seems that usually it's done this way. So we're given the fact that dA dt is equal to 3. And we want to know what is dr dt, so that's the rate we're looking for. We want to know how fast the radius is changing with respect to time, and we want to know that at precisely the moment r is equal to 1.25. Basically, not only the fact that the area is changing is going to affect the rate that the radius is changing, but also we have to look at the particular time or a particular moment. In this moment, we want to know how is that happening when r is 1.25? So basically what we do is we take our area formula, A equals pi r squared, and then we differentiate both sides with respect to t. So the area of the derivative of a would typically be 1, but remember, since it's an implicit differentiation, it would be a times dA dt, and the derivative of r squared would be 2r. So the right-hand side becomes 2 pi r, but then again we have to multiply by dr dt because it is an implicit function of time as well. So then we just plug in the things that we know. So we're going to plug in 3 for dA dt, that's given. And then pi is just a constant. R, we want to know how fast dr dt is changing when that number is 1.25, and then we're just left with dr dt. So essentially, we have 3 is equal to 2.5 pi times dr dt. And then to solve, we just divide both sides by 2.5 pi on both sides of the equation. So basically 0.382, and it's a rate of change of the radius over time, so that's meters per second. That's the approximate value of dr dt. Again, we're just approximating to 3 decimal places here because obviously pi is something that is not going to have an exact value over 3 decimal places. So basically the radius is expanding. At a rate of 0.382 meters per second when r is equal to 1.25. So that's that. All right. So that's the first example. And this general procedure is what we do. We basically try and find the formula and then plug in the things that we know. And take the derivative of the formula, then plug in the things we know. So usually we'll have both the variables that we're plugging in and then also the rate of the change over the variables. So we can kind of summarize that strategy as follows. Summary of related rates. So what is the summary? Well, we want to determine a formula that relates unknowns. Two, we want to differentiate both sides with respect to time. And then lastly, we want to plug in the known information to solve for the given rate or for the desired rate. Okay, so let's look at another example. So one of the most common examples we see in these related rate problems involve right triangles. So right triangles are a common way to solve for distances that are changing between 2 points. Really, the Pythagorean theorem is the same thing as the distance formula. So let's look at one such example. So what does this example say? It says, at noon, ship A is 150 kilometers west of ship B. And then we know that ship A is sailing east at 35 kilometers per hour. And ship B is sailing north at 25 kilometers per hour. So we want to know how fast the distance between them is changing at 4 p.m. So one of the things we'll do here is sorry, that's a question. We will also be using the rates to figure out how far apart the distances are, because we know their initial position, but then we're looking at how far apart they are 4 hours later. That's the specific time. So kind of our picture that we have we have this one. So we have the initial point that they start at, then we have one ship sailing this direction. So we'll call that Y maybe. And then we have the other one sailing, I guess it's sailing east. So we have north and east. So let me just start over. So we have one ship sailing north from the initial position, and then the other one sailing east. So this is a right triangle, and this dotted line right here, the hypotenuse, this is the distance that they're changing. So let's call the distance Z. We'll call the horizontal component X and the vertical component Y. So what are we given? We're given dx dt and dy dt. So we know that dx dt is equal to 35. And also we know dy dt is equal to 25. And then what else? Well, we want to know how fast the distance between them is changing. So we want to know, what does dz dt look like when time is 4 hours, because we're 4 hours later. So one of the things we want to figure out is, what are those x, y, and z values at 4 p.m. So at 4 p.m., we know x is going to be actually, I did do this triangle kind of backwards, because if we look at the problem, let's think about it again. The ship starts out west of, so if we think about the problem again, what did it say? They don't start from the same point. It says at noon, ship A is 150 kilometers west of ship B, and ship A is sailing to the east. So basically, if we look at the ships, ship B is starting off here and ship A is starting off here. And so ship A is actually traveling toward this initial point this way, and the other ship B, is traveling north. So our triangle does look like this. So this is our distance, this is X, this is Y, and this is Z. So the triangle looks the same. The orientation is just a bit different. Sorry, that Z is a little sloppy for my taste. So X, what is it? Well, initially I start off 150 miles west of the ship B, but then I'm moving closer to that point. So X is actually going to be 150 minus the 4 hours times the 35 kilometers per hour that I'm traveling at. So X turns out to only be 10 kilometers at that given point in time. Y starts from this point up here, and it's traveling north, so Y is just going to be 4 times its speed. So Y is 4 times 25, so Y is simply 100 kilometers. And then our final distance, Z, well, we have a right triangle, so we can use those two components. The the Pythagorean theorem to figure that out. So z is going to be 10 squared plus 100 squared, and that's the value of z squared. So z will just be the square root of 10,100, which, if we approximate that with a decimal, is 100.5 kilometers. So let's go ahead and figure out. So what equation relates the variables? Well, the equation that relates the variables is what we used for z. So this is kind of scratch work just to help figure out some of the given information. So in general, we do know z squared equals x squared times y squared all the time, or x squared plus y squared, I'm sorry. And then what we want to do, so this is just from the Pythagorean theorem. So then what we want to do is, now that we have the equation that relates all three variables here, we want to take the derivative of that implicitly. So implicit differentiation says, well, we have three different implicit functions of time, z, x, and y. So the derivative would be 2z times dz dt plus 2y, or equals 2x dx dt plus 2y dy dt. Okay, so now we have our related rates equation that has three different variables, x, y, and z, and also three different rates, dx dt, dy dt, and dz dt. So what we can do, one thing to make the numbers simpler, we can divide both sides by 2, just to get rid of all those 2's. So we really just have z dz dt equals x dx dt plus y dy dt. And then we can go ahead and plug in all of those numbers that we found. So we saw z was approximately 100.5, and then dz dt is the rate that we want to find, so we just leave that alone. X was equal to 10, and dx dt was equal to 35. Y was equal to 100, and dy dt was equal to 25. And now we just solve this equation for dz dt. So we end up with 100.5 times dz dt equals 2,850. And then we just divide both sides by 100.5. So we get our answer. So our answer is dz dt is approximately 28.36 kilometers per hour. So these ships are moving apart at a rate of 28.36 kilometers per hour, which makes sense in terms of is the answer reasonable, because we know one ship is moving at 25 kilometers an hour and the other one is 35 kilometers per hour. Again, they're both not moving directly apart. The largest number that would make sense kind of rationally would be their sum, which would be 60 kilometers per hour, and that would be if they were just moving in complete opposite directions, but that's not happening here. So basically any number between 0 and 60 is going to be kind of reasonable, but moving at a right angle with one moving towards the other, we know it's going to be much smaller than that. Okay. So let's look at maybe one more example that involves this triangle type of thing, and then we'll do a few from the homework next time if anybody has questions. But let's look at this example. So this is also a Pythagorean theorem example, but it's going to be a little bit different. So this example, we have a 10-foot ladder rests against a vertical wall. If the bottom slides away at 1 foot per second, how fast is the top of the ladder sliding down? When the bottom is 6 feet from the wall. So again, this is a Pythagorean theorem. If we look at the picture, we've got some big tall building, and then we've got the ground, and then we've got this ladder. The thing is, the ladder is always going to be the same length. Since the ladder is sliding down the wall, this hypotenuse is never changing. It is always going to be exactly 10 feet, whereas in the previous problem, the distance between the ships was changing. So all three sides of the triangle were changing. In this case, only 2 out of the 3 triangles are changing. So what are we given? Well, we're given dx dt is 1. What do we want to find? Well, we want to find dy dt when the bottom is 6 feet from the wall. So that's when x is equal to 6. So dy dt when x equals 6. So again, the Pythagorean theorem is going to relate them. So what is going on in the Pythagorean theorem this time? We have x squared plus y squared is equal to 10 squared. So notice x and y, the 2 legs of the triangle, are changing, whereas the hypotenuse 10 does not change. So when we do the derivative implicitly, we'll have 2x dx dt plus 2y dy dt equals 100. Excuse me. So when you evaluate 10 squared, it's 100, but when you take the derivative of 10 squared, it being a constant, the derivative is just equal to 0. So what things do we need to find? Well, we're given dx dt. We want to find dy dt. So there's 2 other letters in the problem, x and y. X is given when x is 6, so we need to find y using the Pythagorean theorem. So we know 6 squared plus y squared will equal 10 squared. So we have 36 plus y squared equals 100. If you subtract, we end up with y squared equals 64. So when you take the square root, we end up with y equals 8. So we can replace the unknowns in the related rates equation. We have 2 times 6. We know dx dt is just 1. We have 2. We just found that y is 8, and we're trying to solve for dy dt. So we end up with 12 plus 16 times dy dt equals 0. So we have 16 dy dt equals negative 12. And we can divide on both sides by 16. So we have found that dy dt is negative 0.75, and that's feet per second. So notice it's actually negative because the ladder is sliding down the wall. So that's actually telling us the orientation of that velocity. So the actual y value is getting smaller over time. So when the ladder is 6 feet from the wall, the top is sliding down at a rate of 0.75 feet per second. So we have found the desired related rate. So that'll be it for today. We'll go over some more examples next time. If you have any questions on the homework, please let me know and I can include those in the video. Otherwise, this is Dr. Lennon signing off.